Hello, my name is Gilles Mordant and I'm a PhD student at UC Louvain. I'm going to present to you joint work with Marc Alain and Johan Segers about multivariate goodness of fit tests based on Wasserstein distance. Before moving to the table of contents, I'd like to warmly thank the organizers for setting up this conference. I'll first start by introducing the problem. I'll then move on to the tests that we define. I will then explain how to make the computations required, and I will finally present a few simulation results. In statistics and modeling, there is this very fundamental question that is, does the observed data that I have come from a specific model or a family of models? And to address such a question, you can rely on the following meta approach. You find a metric on a space of probability distributions that is as large as possible, you construct an empirical version of this metric, you find its distribution under the null hypothesis, or find a way to approximate it, and then you perform the test. In one dimension, for instance, the test by Kolmogorov and Smirnov is doing just that. Here, we'll follow this approach, relying on the p-Wasserstein distance. If we define gamma pq, the set of probability measures with marginals p and q, and curly p, the set of borrowed probability measures on Rd with finite pth moment, we can define the p-Wasserstein distance between p and q, both belonging to curly p, as the following infimum over the set gamma of this integral, which is an expectation with respect to gamma of the pth power of the Euclidean distance between x and y. We can now define the test relying on this metric. First, we'll consider an IID sample and the corresponding empirical measure p hat, and the hypothesis that we want to test here is that each element of the sample comes from a certain measure p0. We'll propose to use the empirical Wasserstein distance, that is the Wasserstein distance between the empirical measure and the reference measure p0, as a test statistic. The test will reject if this test statistic is larger than a certain threshold that is calibrated such that the type 1 error is going to be at most alpha. We can prove that the test is consistent. This follows from Varadarajan's theorem that states that the empirical measure converges weakly to the true measure that generated the elements of the sample used to construct this empirical measure, and this, combined with convergence of moments, implies convergence of the Wasserstein distance. Thus we know that under the null hypothesis, the test statistic is going to be asymptotically zero, whereas, under an alternative, the test statistic will converge to a constant strictly larger than zero, which implies consistency. But often, in statistics, we're interested not in a simple null hypothesis, but in testing that the data that I have comes from a family of models indexed by theta belonging to a big theta, a metric space, and these thetas are usually called nuisance parameters. And to perform such a test, we suggest relying on the Wasserstein distance between the empirical measure and an element of the family that corresponds to a certain estimator theta hat. The test will again have the same form, that is, will reject if the test statistic is larger than a certain threshold. We can prove consistency again. We need that the map from big theta to curly p is 1-to-1 and continuous with respect to the Wasserstein distance, and we also require this estimator of theta to be weakly consistent locally uniformly in theta. With this, we can prove that uniformly in theta the test statistic will converge to zero, and for every p not belonging to the model, provided a small technical condition, we'll have that the power is 1 will have consistency. It now remains to understand how to compute the empirical Wasserstein distance, that is the Wasserstein distance between an empirical measure and a reference measure. This is often done relying on a dual formulation. This formulation appears on screen. And what you can see in this problem is that there are certain cells, here, that are indexed by a weight vector psi, which will determine the size of these cells. And in the very particular case where p is equal to 2, these v psi j are Laguerre cells. And they are particular because their boundaries are defined by linear constraints. Many algorithms were proposed to solve this problem. The one by Merigot, the one by Geneve and co-authors, the one by Hartmann and Schumacher, are a few examples dealing with different cases or different approaches. Let us now have a look at a visual representation of the optimal solution in a particular case. Here we have the points that were used to construct the empirical measure, and here are many realizations of the reference measure Q, in this case a Gaussian. And you can see that the solution involves a tessellation, the cells that were these V psi j that we defined before, and these cells are such that the costs of transporting the content of each cell to the corresponding point will overall be minimal. We will now evaluate the performance of the test in a simulation study. But first, we'd like to compare our test with two other ones. The first one is the one by Rippel-Mungenstern, and it's based on the fact that for two distributions coming from the same elliptical family, there is a closed form formula for the two Wasserstein distance. What they proposed is to plug in estimators of the mean vector and the covariance matrix in this closed form formula. Then, we also want to test and evaluate the performance of the test by Chmaladze, which is based on a supremum of the absolute value of a transformed Brownian bridge. This is a generalization of the test proposed by Kolmogorov and Smirnov. In the first setting, we consider a simple null hypothesis that is a centered isotropic bivariate Gaussian. We let the correlation parameter vary, and what we observe here is that the test by Rippel-Mungenstern is performing better than the other tests. It's not surprising, because the test is in a sense parametric, as it only relies on the mean and the covariance matrix. Still, the power of the test based on the Wasserstein distance is not way lower. Now, we keep the same null hypothesis, but we consider a distribution that has a t-copula, standard Gaussian margins, and we let the correlation parameter of this t-copula vary. There is thus no setting where we are under the null hypothesis. And here we can see that the test based on the two Wasserstein distance clearly outperforms all the other tests. In 5 dimensions, we consider a distribution that has an independence copula, and all its margins are t distributions with 25 degrees of freedom. We now let the number of degrees of freedom of the margins vary, and we observe that the tests based on the Wasserstein distance are clearly outperforming the test proposed by Chmaladze. We now keep the same null hypothesis, but we induce dependence between 2 of the 5 margins. This dependence comes from a t-copula, and we let its parameter vary. So here again, there is no setting for which we are under the null hypothesis. And again, we can see that the tests based on the Wasserstein distance are clearly outperforming the test proposed by Chmaladze. Location and scatter are a particular example of nuisance parameters that you often encounter in statistics. In this case, instead of working with the empirical measure relying on observations, we propose to use an empirical measure relying on residuals. Residuals in the sense that we will empirically center and rescale the observations where the scaling is based on the Cholesky square root of the empirical covariance matrix. The test statistic that we will then use is the same as usual, except that the empirical measure is now replaced by this empirical measure on residuals, and the test will again reject if the test statistic is larger than a certain threshold. A particular location scatter family that attracts a lot of attention is the Gaussian family. Here, we place ourselves in the bivariate case, and we will compare the test proposed with the test by Royston, the test by Henze and Zirkler, and the test based on the energy distance that was proposed by Shekeli and Rizzo. The alternatives that are considered are distributions with a Gumbel copula and Gaussian standard margins. And we can see here that the test based on the Wasserstein distance is outperforming the others. In the second setting, the alternatives that are generated are based on the distribution whose copula is the independence copula and whose margins are a Gaussian margin and a t-distributed margin. We let the number of degrees of freedom of this last margin vary, and we observe the performance. Here, the best test is the one proposed by Royston, but it does not keep the level alpha. Still, the test proposed based on the Wasserstein distance exhibits a quite good performance. If we move to a Pentavariate Gaussian family, and we consider all the margins to now be t distributions with a certain number of degrees of freedom, we observe the same behavior as before. The test proposed by Royston performs better, but does not keep the level, whereas the test based on the Wasserstein distance are second best in class. And if we again change the dependent structure, relying on a Gamow-Coppola for two of the margins, we see that the test relying on the Wasserstein distance again has a good performance. So here were a few of the simulation settings that we considered. I invite you to have a look at the paper on arXiv for more information, and I'm really looking forward to answering the questions that you have during the Q&A session. Here's a list of a few selected references. Thank you very much.